have a movie theater in the campus for the students. And once in a year for 15 days, we used to have a movie festival. So we used to have one new movie every day. So for those 15 days, you have a dinner in the campus in your hostel mess, and then start casually walking towards the theater and then sit there and watch a movie, come back and sleep. So it was almost like the surreal experience where we had lunch just now and I see people slowly walking in. I remember my college days. Anyway, thank you very much for coming. Is the audio clear enough? Can you guys hear me? Yes. Okay, cool. Not picked up as much. For example, the AI models that make numeric predictions or AI models that can look at an image, still image or a video and make a prediction, the accuracy rates are very, very high. Somewhere 80, 90, 95, 98% accuracy rates too. But in text processing, the accuracy measures are measured in terms of rogue factors or blue factors. You need to go check what those factors are, but it makes how closer is the model coming to make a prediction about the text which is comparable to human beings. And that's measured in terms of rogue factors or blue factors. That's only still in the range of 40, 50. Higher is better. So it's like almost like a percentage accuracy. It's 40%, 50% accurate at this point of time. I'm going to show a bunch of experiments being done. I will also explain some very, very fundamental building blocks of deep neural networks, which would be used in summarizing the text, and I'll talk about that. In 1 hour session, I will go from as simple definition of what is RNN, and I will go to the extreme definition of defining certain architectures for defining text summarization. Obviously, in 1 hour, going from the left to the right, I think it's not that easy, so I will be jumping certain topics. And at any point of time, if you have any questions, you can interrupt me and we can talk. Otherwise, you need to refer to my boring blog I suggested for you guys to read. But before we start the presentation today, I had a mathematical problem and I could not solve it, and I thought you guys can help me in solving it. Okay? Yeah. Typically, yes is this way. Let's say there are two cities, city A and city B. And two cars start from one from city A and one from city B. The cities are separated by 100 kilometers, and each car is driving towards the other at the rate of 50 kilometers per hour. Okay? So far so good? A bird flies from city A at the same time at the car A from city A starts at a speed of 80 kilometers per hour. Flies all the way, it touches the other car, immediately turns back and starts flying towards city A till it touches car A, and then immediately turns back, fly towards the other car, keeps on doing till both the cars touch each other. How many kilometers did the bird fly? Who said 80? Okay? That's 40. Take a guess, and I will tell the answer at the end of this presentation. And someone said, the best way of keeping an attention of the audience is ask a very simple question at the start, and don't tell the answer to the end. So I'm going to tell you the answer at the end. Today is Deep Networks, and we're going to talk about mathematics a lot. And also, how you can use your brain intelligently. Before I get into deep networks, I'll give you a different story about how you can really intelligently use your brain to solve a very complex problem. There's a book written called Recurrent. I forgot the name of the author, I think it's Stephen something, a few years ago, around 10 years ago. Have you heard of the book, Economics? No? If you have not, I think you should read the book. I think it's a nice book. I don't know if you have any book library in this here in Hyderabad. I think if it's not, I think you should buy a book and read. The authors were explaining an interesting facet about terrorism. They said terrorists who wants to commit a terrorist activity have very peculiar behavioral style. Whenever they draw money from ATMs, they always draw small amounts. They actually draw multiple and frequent amounts, but always small amounts, which is in such a way that it doesn't attract the attention of the bank if it's tracking. They always go to different ATMs, not the same ATM. They will try to go to ATMs which don't have cameras, but many ATMs do have cameras. Many times they are wearing caps or other facially camouflaging things like a big beard or a cap. And they don't have any friends, they don't have too much of, even when they sign a contract for a lease or an apartment, it's for a short duration. So anti-terrorism organizations, when they're tracking such terrorists, they actually know exactly this behavior. So these authors made an interesting recommendation to those terrorists. They said, if you are a terrorist and if you have this behavioral pattern, please know that the cops or the police would know your behavioral style. Just to confuse them, do the following. And that is, buy a long-term life insurance policy. Because anyone who's trying to do a terrorist activity, apparently, there's no way you will buy an insurance policy because who's going to get it? Because any person, if I put your name on that, once I die, what's going to happen? He's going to be caught, right? So no one would buy an insurance policy. And I said, just to put off or confuse the police, buy an insurance policy. So when the book came, when it was released, many anti-terrorism squads in the world, they read the book and they got very irritated with this authors. What are you trying to do? Are you trying to help this terrorist? So they got called for a meeting. And they said, listen to our logic first. The behavioral patterns, what you are tracking, are well known to you guys and well known to them too. But now, a terrorist who's trying to commit terrorist activity, who really wants to avoid being detected, if they listen to our idea, they actually will go buy an insurance policy. Now you have an additional behavioral habit. They draw small amounts of money from ATMs, go to different ATMs, always have a cab, they don't have any friends, but suddenly they're buying an insurance policy. That's a sure shot identity that this person is your terrorist you're going to track. So then, of course, all these terrorist anti-terrorism organizations are very happy, and it's a very happy ending. There are similar such mind-bending stories in the book. I think you should read the book for context. But with that story, let's talk about text summarization. Number processing or image processing in artificial intelligence is pretty straightforward because you're feeding computers with numbers. In the image processing side, what are the numbers you're processing? You're feeding the pixel value of the images. So in both the cases, it's just numbers. You're giving the numbers to the computer and the computer is processing. So it's straightforward. But how do you do that when you're doing text? How do you convert a text into a number? Because unless you convert a text into a number, you'll not be able to process it. And all your ANNs, artificial neural networks, will not be able to work on this. So, before I get into text summarization, here's an example of a summarization. So this is an original text. And these are some of the models that have been proposed in the last few years. I'll explain some of these, how they work. But many of these models have been successful in converting large amount of text to a small text. So let's talk about what is the purpose of text summarization. There is a subsidiary topic called topic modeling. If you write an article, you want to fit this article into certain topics you are interested in. Let's say you sign up for a new news article, and the first time when you log in, the app will ask you, what are your likes? Do you like sports? Do you like movies? Do you like Bollywood? Do you like action movies? You pick some of the topics. So when the model understands what topics you're interested in, you feed in the articles that's coming in from various news organizations. The ANN would do something called topic modeling. It actually identifies what topic this fits into. So if you have, let's say, an event that has happened, a cricket event today that happened, and you want to find out the traffic, this news item regarding cricket event could fall into sports, could fall into the traffic situation, or could fall into the reflection of the economy, or maybe just the economic activities itself. So the model can intelligently find out what topic this falls into. So text summarization can be used for topic modeling. Text summarization can also be used for question answering. So you ask a question, tell me what would be the route to go from point A to point B. It actually explains what are the various things you can do. Or tell me, how do I compute the answer for this question? It actually gives an answer for you. So it's a variation of question answer is also text summarization. Another use case in a corporate world, like a company like Hexagon, is when you have a large amount of information about a product, but you want to actually get the essence out of it. Or let's say you're a salesperson and you have just joined the company and you're talking to a customer asks you a question about a product that was 1 year old, 5 years old, and information which is not known to everyone. You can actually have an ANN, Deep Network, we actually can ask a question. It can summarize the information what you're looking for from a bunch of documentation and gives you an answer. So the applications of text summarizations are many. But at the fundamental level of text summarization is you have a large amount of text and you have to output a small amount of text which reflects the message in the large text. And if you draw that to the extreme, it can be topic modeling, it identifies the topic it belongs to, or it can even be used to identify the title for your news article or for your story. There are multiple ways of converting text into numbers. The least favorite is called one-hot vectors. Even though I say least favorite, according to the industry information, in my personal experience, it actually worked really well for a couple of my projects I've done in AI, and I'll explain that to you in a minute. So one-hot vectors is one way of converting words into numbers, and this is how it works. Let's say you have a vocabulary of 1,000 words you're going to be using for your text summarization model. If you organize all the words in certain order, doesn't have to be alphabetical order, in any order you keep. So you have 1,000 words, one next to each other, and you have a vector where all with 1,000 zeros. For each word, let's say pick the first word in the vocab and replace the first zero with a 1. Now that vector becomes the reflection of the first word. The second word, similarly, you replace the second zero in the original all zero vector by a 1. That is 0, 1 and 998 zeros after that would be the vector for the second word, and so on. This is called one-hot vector. Now, a couple of years ago, in 2016, the most commonly used vector conversions from word to numbers is called word to vec. Engineers, software engineers are not really very creative with giving names, so it's called word to vec. And it's a simple algorithm, and I won't explain the algorithm today, but you don't actually have to build a software for the algorithm, just a single line API call. When you're using a framework like, let's say, TaskFlow, it will convert text into vectors. The reason I would say one-hot vectors is one of the works really well is around 2 years ago, I was working on a text summarization project, actually question answering project, which is a variation of text summarization. And the question answering model works the following. You give a large amount of text, the model understands the text, and then after that you can ask a question, and then the model gives an answer. I don't know whether I told you the story when it comes to comprehension of text by AI model, Sally went in the kitchen, John went there too, Sally said a hi to. As a human being, we know Sally is saying a hi to who? John. But nowhere I said John is in the kitchen. I just said John went there too. But AI models can comprehend the text and then understand what's actually happening, like a human being. So I was developing a question answering model. It's actually open sourced in GitHub if you guys want to go check it, you can check that. And I was looking for a text, a story, what I can feed into the model, and I found an online story of Mahabharata. So I actually picked it up and fed it into the model. It actually started giving good answers. I think it was 78% accuracy, it was giving answers. There I tried multiple approaches of converting words into text. I used word-to-vec. I also used another method called GLOVE, G-L-O-V-E, it's global vectors. Shortened version of global vectors is GLOVE. And I also used one-hot vectors. The accuracy rate of the model was higher. Architecture being the same, when I used one-hot vectors, the accuracy rate was higher. So I personally believe one-hot vector still works, but many times I've seen in examples, when you use text and you convert it into text into vectors, the most common and most easy to use is word-to-vec. W-O-R-D number 2 B-E-C, word-to-vec. So I'm actually going to be, in the next few slides, I'm just going to introduce certain building blocks of AI in the context of text processing. And some of the building blocks will be used for other areas too, but I'm focusing purely on text processing. So I'm building a case slowly on how to develop an artificial neural network to design a text summarization model. There's a guy by the name Andre Karpathy. He wrote, he developed a text processing model a couple of years ago and wrote a blog on this. He created an AI model that would recreate the behavior of Shakespeare. You would have heard of Shakespeare? Yeah, the guy who used to, no. Anyway, he used to write a lot of novels. The AI model started writing text as if it was Shakespeare's novel. Of course, the intricate plot was missing in the story. But some of the names it was picking, the font style the model Shakespeare used to use, the model could understand that. Even some of the notations it uses at the end of the names and the dialogues which each actor says is shown as a separate paragraph. Sometimes some of the words it picked up, they would be ruled after this chamber and my fair news began out of the fact. Even though it's not really completely grammatically correct sentences, he could achieve this with very few epochs, and he said I stopped running a model after that because I was not sure how long it's going to go, but he could achieve this artificial intelligence model of text summarization where it actually, he trained a model on writing Shakespeare novels. Here is a real example of summarization. Metro Goldwyn Mayer reported a third quarter net loss of $16 million due mainly to effective accounting rules adopted this year. MGM reports 60 million net loss on higher revenue. This is actually an output of a model. So you have large amount of text and you have to summarize that. Historically, there are two types of summarizations. Something called extractive summarization. The other one is abstractive summarization. Extractive summarization means you look at the text, pick a few words or pick a few sentences which are very, very salient, which reflect the true message of the passage, and put it together, and that becomes a summary. So the model, the expert system in this case, or AI model, is actually picking the words or sentences as is, but not the entire set of sentences, only a few, and then making the summary. That's called extractive. A couple of years ago, 10 years ago, there were models available, there were rules-based engines, there was more of a pattern matching and extracting the words. They were not really successful, they were not generalizable models. The other way of summarization is called abstractive. So if in this example, Metro Goldwyn Mayer reported a third quarter net loss of $16 million due mainly to, whereas and the summarization says MGM reports $16 million net loss on higher revenue. The word higher revenue doesn't exist in the input. Model actually felt those are the two right words that need to be created and put for the context. So the model understood the entire message in the input, found out a better way of representing in a shorter format and gave an output. Now, in text summarization, especially even if it's abstractive summarizations, I'm going to talk about some techniques are very, very simple enough to actually create summarizations. Initially, in 2016, 2017, the models which were popular had lots and lots of problems, and I'll talk about those problems and how my last paper I'm going to be sharing today, this slide set will be about a paper released I think in May of 2018, a couple of months ago, and how that's the latest research to show how summarization is to be done. Okay, this is another example visualization of looking at text after you convert them into vectors. Now, if you decide the vector should be of 100 dimensions or 200 dimensions or 500 dimensions, you convert the words into vectors of, let's say, 500 dimensions. And if you plot these vectors in a 500 dimension space, now I don't know if you ever actually encountered that high dimensional space. You know what a two-dimensional space is. You have x and y, and for three-dimensional space you have x, y, and z. But if you increase the number of dimensions, it is difficult to mentally imagine how that space looks like. If you have a 500 dimension space, it's not that easy to visualize. For example, if you, on an xy, on a two-dimensional space, if you look at three different dots, you can look at it and with your eye you can figure out which of these dots are closer to each other and which are not. Maybe in three-dimensional you can figure out, but it becomes a little confusing. Closer to each other means how? Then you have to use the x and y and z factors and the mathematics to find out which one is closer, which is not closer. But when it comes to 4-dimension, 10-dimension, 100-dimension, 500-dimension, it becomes more difficult. So there's a technique called t-SNE, which will do the dimensionality reduction and posts it on a two-dimensional space. This is a t-SNE of various words on the screen. This is, okay, let me go back first. Here, what is the purpose of a t-SNE view of word embeddings? There's one fundamental objective. You can see, after converting the words into vectors, words of similar nature, they appear close together in the 500 dimension space, and the same thing can be seen in a 2 dimensions in t-SNE, using t-SNE. So all the capitals of the city, of countries, all the country names, all the names of food, all the names of vehicles, all appear together, showing the fact that your conversion into the vectors is actually retaining the essence of the meaning of the word too. It's actually retaining the essence of the word. It's just not a jumbled up characters. That's the primary purpose. So when you do one-hot vectors, that is one thing which you do not capture. The cat sat on the mat sat on the cat sat mat on the. If that happens to be your vocab, using one-hot vectors, the cat will have the same vector or different vector depending upon how you arrange the vocab. It does not capture the essence of what cat stands for. Whereas in glove and word to vector actually captures the essence. And that's what was many months AI experts were struggling with. How do we capture the essence of the word? For example, the cat sat on the mat. The comes first, cat comes first, the subject comes first and the object comes later, the verb comes somewhere in the middle, which is typical English language structure. That essence needs to be captured. Someone did the experiment of taking all the Wikipedia articles, instead of words, they took the entire passage or the article and created a word embedding of all the words that appear in a single article, and made maybe a 500 dimension vector. And then when you extrapolate that into a t-SNE, you can still see all the words related to, all articles related to science, all the articles related to films, all articles related to albums, they fall closer together. So in other words, not just the word vectors capture the essence, but even the articles or even passages or sentences retain the essence when you convert it to vectors. Okay, here is the most often repeated word. RNN, recurrent neural networks. Recurrent neural network is that type of artificial neural network that takes a series of inputs which occur in a sequence over a period of time. In other words, time is an essence for this data. So there has to be a sequence. And one influences the other, which in turn influences the other, and so on. And so they have it's called temporal data. So it is over a period of, for the example I gave you yesterday regarding patient data. If you have 9,000 patients, patient 1, patient 2 are not related, just there are two independent data points. There could be some other relationship between patient 1 and patient 2, maybe they are from the same family, but the relationship between patient 1 and patient 50, patient 1 and patient 100, there's no connection. They don't appear in any sequence per se. And actually, for classic machine learning, you want to have that data which is independent of each other. The moment they are connected with each other, for example, if you're predicting which could rain tomorrow, and if you take the factor of being sunny and also cloudy, if it's cloudy, it's not really sunny that day. So, cloudy and sunny helping you making a prediction that it's going to rain is not really a good model, because the input data, one of them is influencing the other. And you need to discard that, and that's where I think the domain expertise comes in. But here in RNN, you've got to have a sequence. You've got to have a sequence of input that's coming in. I mentioned yesterday, I think, after lunch, I think it's always a difficult situation to explain. And I can tell you a couple of stories, but then I'll be taking away the time which I would like to use to explain ANNs. So let's do for just 1 minute, let's do the following exercise. If you don't mind, please all stand up and then stay standing for the next 1 minute. And I'll continue to talk, and I'll tell you when to sit down, and then you can sit down. Hopefully that will make you come out of your... and also it will tell you, standing here for 1 hour, it's not an easy task, and hopefully you'll appreciate that too. So yeah, hopefully I think now you can still see, and I'm sure some people they cannot see, but so apologies for that. But let's see, hopefully this comes out of, make you come out of your slumber. So RNN takes these vectors of words you have taken. You input one after the other in the same sequence. And the model RNN takes one after the other. Now here you see on the left side a single RNN which is taking an input called X and it's an outputting O. You see this a loop which is looping back. What it means is at every timestamp t is equal to 1, t is equal to 2, t is equal to 3, or in other words, ti is equal to t1, t1, t2, t3, t4. The model will continue to take the input. So if you unfold this looping structure, it's the same neural network which is taking x t minus 1 as an input at time t minus 1, does something with the data and gives an output over t minus 1, and at the next timestamp at xt, it takes the new input xt, gives out a new output. You know what would be amazing is, I saw a few people be yawning and that's why I asked you to stand up. What would be really mind-boggling for me is if you stand and still yawn. But hopefully I think you're not going to. Please sit down and then you can sit down. Laughter. Yeah, sometimes I always think, okay, obviously SK, you think you're very intelligent, you just wouldn't stop me from yawning. I'm going to stand up and yawn too. But hopefully I think you come out of here somewhere. So for every input, RNN multiplies or does some mathematical manipulation on the input using a matrix, let's call it as U, and it creates something called a hidden state. For ease of understanding, let's say hidden state is nothing else but a transformation of your input vector into a different vector, because you have multiplied the input vector with certain matrix, a 2x2 matrix. Okay? I'm assuming you know what a matrix is. And whenever I say assume, I always remember assume means you make an ass of you and me. If you break the word assume. So I don't want to make an ass of you or me, but I'm assuming that you already know matrices. So you take an input matrix and you multiply that with the input, which is a vector, and then you create a hidden state. And that hidden state is further multiplied with a different vector, v, to give an output. So on a very fundamental level, every neural network, RNN, takes an input, multiplies that with the matrix, creates a hidden state, keeps that information for itself, but if it wants to create an output at that timestamp, it takes the help of another matrix and then creates an output. What are these matrices? What is this output? Because at the end of the day, when I say output, this is also still a matrix. It's just a bunch of numbers. But I'll explain that in a few minutes how the output is a useful output for you. But for now, let's keep this in mind. We take a matrix, we take a vector, multiply that with a matrix. You have another vector, which is actually called a hidden state. Hidden state is historically used, denoted by h, small h. But in this case, we're showing S. I've seen a few papers a couple of years ago, they were using S and also C. But nowadays, more and more papers are using H as a notation for hidden state. And O is the output. This is the entire explanation of RNN. RNN takes a sequence of vectors, processes it, and then gives an output. Now, what is happening with the hidden state? Hidden state can be explained as if that's the memory of the neural network or the intelligence of the neural network, because it's taking your inputs one by one and assimilating that input. So when you say the cat sat on the mat, after the first word, the RNN understands it's been given a word called the, and then after the second word, the RNN understands it's got a word the cat. So the hidden state after the cat will be a jumbled up formation that shows there are two words called the cat. And if you give a long sentence, at the end of the entire sentence, the memory or the intelligence of RNN actually captured the essence of the sentence you've given. This is extremely mind-boggling. When I started reading about RNNs, I can't imagine an artificial intelligence model called RNN takes a complete sentence, understands like a human being like you and us. And the funny thing is, it does not know anything about English language, never even heard of English language. But the more you start feeding in, I don't know, maybe it took less for you, but it took a lot of years for me to understand English. For an RNN model, if it's a language model you create, a couple of weeks to 3 weeks, running on a few GPUs, will understand the entire English language and understand so well that you give an incorrect sentence, the model will tell you where the sentence is wrong. Or if you give half incomplete sentence, it starts completing what would appear as the next word or the next word. You have a question?
You mean to say that if I give any language, for say Telugu language sentence, then also it can able to understand that content of it?
Yes.
How is it possible?
Yeah, there you go. I can give two answers for that question. How is it possible? If the vector conversion of the words is based on the enough vocab, and use the algorithms which I did not explain here, how you use glove vectors and word to vec. It actually takes, for every word, it takes 2 words before and 2 words after. You can expand the window, that's called window of 2 words. You can expand that to 4 words, 5 words, but then become computationally expensive. But they say 2 words before, 2 words after, and the word total of 5 words. And you start converting that using certain algorithm approach. You can convert it to vector. So every word actually understands these are the 2 words that appear before me and 2 words that appear after me. And the same word, if you look at multiple times, the same word will come with different words before and different words after. So it starts understanding what words normally come in front of me and normally come after me, and what words will never come in front of me and never come after me. And you give enough data and then it understands it. So that's one answer for your question. Second answer is, that's the magic. Neural networks sometimes cannot explain what's happening. That's why there is a new area of research. If you really want to do PhD, this is a topic for you. The new area of research called explainable machine learning. People are worried, especially GDPR is a new law that's been passed in the European Union. Companies have to explain why you are making a recommendation to your customer. Companies have to explain why you are recommending this medicine treatment for your patient. You have to explain why you are telling this customer to buy a book. And sometimes you can't explain. And I might have mentioned this example yesterday, that there was a job recommendation model that was created which was recommending all the C-level executive jobs only to men and not to women, even though they were equally qualified women available. And the reason for that was the data, even though the architects of the model never told that gender is a factor, model thought gender is a factor because based on the data it's coming in. And no one figured out when they were training the model. When it started showing in the production system the wrong suggestions and someone pointed it out, and that's when the architects of the model figured out, oh my god, this model is making the wrong assumption. So there's no way of testing the model in that sense. Actually, I have a philosophical take on what software in the context of artificial intelligence means. Let's say you're developing, you're all software engineers, right? How many of you are software engineers? Good. You guys, yeah, only one hand after that. If you, let's say, you're defining a new model, new software solution for the office, when you come in, you flash a badge and you open the door. Let's say you're defining a software solution for that. So you have a scanner, it checks the chip on your badge, sends a signal to the server, it checks an existing database, brings back and says, yes, this is a valid one, and then sends a signal to the lock on the door, and the door unlocks. This all can be sequence of logical sentences. If, then, else, or while, whatever. You can actually have multiple sentences. English, the language, whatever you use it, you can use those sentences. But in the context of AI, what is software there means? Software is a bunch of numbers. The artificial intelligence model is nothing else but collection of weights. Weights are nothing else but numbers. So the entire software or the model is millions of those numbers together. And when you give a new input, you just convert the input into number and give it to this model. The model will do some magic in that, and then at the end of it tells you whether this is a cat or a dog. So in the context of AI, That's why it's called software 2.0. The software is not the traditional software you guys have been using. And hence the traditional testing methodologies, designing methodologies, efficiency improvement methodologies, optimization methodologies on AI model is entirely different. Because you've got to understand what's happening. So going back to your question, it is sometimes magic. Anyway, that's about RNN. So just before I go to the next slide, RNN is a neural network which takes a series of inputs and then keeps on remembering, internalizing the information you're giving. And when it's ready, when you ask, okay, now tell me what did I tell you? The model will start telling you what it understood. You give a sentence, the catch out of the mat, and then say, okay, I gave you the complete sentence, now tell me what I told you. It actually starts telling you that. And I'll show you how to do it. I don't have a slide, but you have the RNN. This is another type of RNN called LSTM, long short-term memory. Long short-term memory, LSTM was a more of invention in 2015, around that time. But whenever I talk about LSTM, the RNN in 2015, 2016, aren't you guys amazed how recent this entire technology is? So in other words, I think in your lifetime, you see a world without AI, and you would be seeing the world with full of AI. Everywhere you go, AI. I think the next 4 or 5 years, you would be, even today, the moment before 8 a.m. or 9 a.m., unless you wake up at 8 a.m., that's before 9 a.m., you would be having AI touch you at least 10 different ways. Whether the moment you pick up your phone, getting your text, getting your email, the spam detector, and checking the weather, the GPS, or if you're trying to place an order on an online e-commerce site, any of these things you're trying to do, you are actually having AI touch you at least 10 different ways within the first 1 hour of the day. So it's amazing, things are changing. So LSTM was invented in 2016-ish, and the reason for that is RNN had one problem. You give a series of inputs to RNN, it starts internalizing, and then when you start asking, okay, now tell me what to tell you, or tell me the translated version of this English sentence into Telugu or Hindi, or whatever language you pick, it starts translating. But they found there is a limitation on the number of inputs RNN can take before it starts forgetting. I don't know about you guys, if you give me 10 sentences, I would definitely forget the first sentence by the time you come to the 10th sentence. So RNN, they found after the 10th word, 9ish, 10th-ish word, the model starts forgetting. Or the amount of memory about the last word is very high compared to the amount of memory it has on the first word, or the second word, or the third word. So it's actually gradually remembering the most recent ones and gradually forgetting the most far away ones. And they said this is not going to work because 7 words. 7 is the golden number for our RNN. They said it's not going to work, so we need to actually have a different RNN which actually can remember us for a longer period. So they came out with LSTM, which is actually long short-term memory. Except the mathematical equations. I'm actually going to explain these mathematical equations. And if you haven't brought your pen and paper, I'm going to ask you a quiz at the end of the 1 hour. How this works, but this here, because of these extra mathematical equations here, the model is constantly not only internalizing the information, but it's also thinking, what information should I actually internalize and what information now I can forget? So you have, compared to RNN, there's only one gate, like one input and then one transformation of the input, and then comes the output. There are multiple transformations of the input. You have xt that's going in, but there's a lot of mathematical equations. I will not explain the mathematical equations now. I'm checking my time too. I took unusually more time for my introduction, but I'm not too worried about that. It does a lot of mathematical computations and still comes out with hidden state. So HT is the hidden state which you should be worried about. Excuse me. And similar to RNN output where you have a hidden state, even the LSTM has a hidden state. The hidden state is a reflection of what you've given inputs for. Now there's a famous professor, I've got the name of the professor at NLP in Stanford University. According to him, now it can actually go to as long as 70 words. You can actually take 70 words and still wouldn't forget the first word after reaching 70 limit. But then if you start putting more, then it starts forgetting the initial words. If you extend this RNN or LSTM, except the difference in mathematical equations, RNN and LSTM work in the same way. LSTM has bigger memory, hence remembers more mathematical computation, hence you got to be careful when you're using LSTM. You don't want to use LSTM even if it's not required, because there's a lot of mathematics happening. Instead of one transformation, you have 4 different transformations happening in LSTM. If you extend the LSTM, you have a series of inputs. So the same RNN, you give an input A, B, and C, and then you have an end of sentence input. For example, typically your end of sentence token could be a period, or could be a special character you tell the model, and that's when you're signaling the model that, okay, I've done with my inputs. Now it's your job to do things, what I've told you to do. And when you give the end of sentence input, it starts outputting. What is its output? Output is what you have trained the model to output in. For example, if you have done a translation model, you give an input in one language, it starts outputting in a different language, whatever you trained in. If you're given, it's a summarization model, you give a large amount of text, it starts outputting summarization of that text. So, and if you ask, if it's a question answering model, you give a question, reads the question, it also already understood what the whole story you've given and starts outputting the answer. So it takes a bunch of inputs along with the end of sentence token and then starts giving output till it creates end of sentence token. That's when the model is telling you